So today I want to speak about new works that we developed, and it is about laser ablation propulsion. So the idea is to use high power pulsed laser irradiation and to see what kind of advanced experiment investigation we can develop. So all these beautiful works was possible because of colleagues, so from, of course, Europe, and also with Photonic Associate, Claude Phipps, because we want to comfort some idea or some new idea in order to think about new history and on laser propulsions. So why we want to focus on that, and for what? For first of all, we have to be concerned about what was done in the past time. So from years ago, as you can see on this slide, we have a beautiful history of laser propulsion. So the beginning of the story was with Kontrowitz in the 17 years, as you can see, in order to make a kind of vaporization of the surface and then to give a kind of mobility to the materials with some ejecting mass. And then this new idea was also to think more and more and to make propulsion. So for that, we can see that we have new works that were developed with Mirabeau and all. And why is so important, for example, the test of Mirabeau, because it was the first experiments that give us the first idea to give a maximum of altitude to some materials, some active. I wanted to show you two examples what's done with Mirabeau. And the first was in 1797. So it was able to have a vehicle of about 50 grams and with a maximum altitude with about 30 meters. And you can see here the laser that we use at that time. And then the second experiment that was done, you can see that the vehicle was more or less the same mass, but you can see that the maximum of the altitude was higher, almost doubles. But you can see that it was possible to have this maximum of amplitude when you are also able to think about new design, about materials and about systems. And why we were concerned about this laser ablation? Because now, as you can see, we have from about 20 years ago, we took concern about Agency Debris Committee, and we can see that we have a first space debris guideline. And you can see that from more and more we are going in the time, more we have an evolution of number of objects. So the number, the area, and also the mass. So this number of objects in the space is always increasing. And that can be now a big problem because they can make some collision with some satellites that they are ongoing, that they are working, and that we use, for example, with our mobile phone. So we can see that nowadays we have a big challenge about this space debris, and we have to think about how to remove or how to change the direction of this kind of debris. And the idea is how to use laser ablation in order to give some idea to be protected about this space debris. And for that, we have to be more concerned about laser ablation and to more understand how it works. So here it's just a short explanation about how laser ablation is working. you can see that at first we have to keep in mind these two pictures on the left side on the slide, the A and B illustrations. So they are very important because they give us the stage where it's important to have the phenomena of laser ablation. At first, we have the heating part when we have the laser in interaction with the object, and then we have what we call the vaporization, and then we have what we call the plasma effect. And then why all these stages are very important? Because they are connected with one parameter, what we call the coupling coefficient, the CM. And the CM estimation is very important because it gives us the number of a parameter about the ablation pressure or the momentum that we can calculate the energy that can give mobility to the object. And then you can see that this parameter, these coupling coefficients, have a maximum, as you can see. And the problem is how to find out this maximum of the CM, because it means we do not need too much intensity, but we must have a minimum of intensity to reach this CM maximum. So this one is very important to reach because it can give us the best conditions to give the propulsion to our materials. So it is one challenge. The second challenge is, of course, what kind of object and what kind of materials and what kind of laser that we can use. So we can see that we have a lot of open questions and a lot of opportunities in order to make this laser ablation propulsion and also to find solution. So now if we wonder about the materials, what is important is when we want to make this calculation of these coupling coefficients, we must keep in mind that this coupling coefficients is also connected to the mass that will be ejected. So it is the parameter M that you can see here. And this parameter M is connected to what we call the specific impulse. So you can see that we have three main parameters to keep in mind. We have these parameters of CM with momentum coupling. We have the mass ejected, and also we have the specific impulse. So we have these three main parameters that we have to keep in mind if we want to specify this laser ablation propulsion's efficiency. And then if we look at the literature, we can see that we can have a lot of possibility to connect this laser ablation of materials. So it can be liquid, it can be metallic part, but also you can see in this diagram on the right slide, it can be materials, polymers. For example, here you can see that a promising polymers, that the name is POM, it is the polyoxymethylene, and these polymers can give us new interesting challenge in order to propose new materials to promote the laser ablations and to select the best, more or less the best materials and laser conditions. So you can see here, it was a small demonstration that we did, but you can see that we have to always think about how to optimize our data. So now let's go to the details and let me give us two experimental campaigns that we did with HiLASE. And in order at first stage to calculate these coupling coefficients, so the demonstration that I want to show you today will use a pendulum and it will be on Perla-B. So I will show you how we did and what was the first result that we can obtain by using the Perla-B energy, and also by playing with materials. And also, the second example that I want to show you today is about BIVOJ experiments that we did. And this is a demonstration about what we can do. And then with these two examples on Perla-B and on BIVOJ, I will explain you them on material focus and some special analysis or hypotheses that we can do nowadays. So first, I will speak about the first experiments we did on Perla-B. And the idea here was to calculate this coupling momentum. And for that, you can see on that picture that we have to develop some special condition in order to calculate these CM parameters. First of all, we have to develop or to use what we call a vacuum chamber. So it is the blue one, as you can see on this picture. And inside this vacuum chamber, we put inside this pendulum. I will show you on the next slide what was our pendulum. But you can see on the right side on this slide, you can see here the schematics of the installations, more or less. So you can see the laser beam, you can see the target, and then the target is holded on a pendulum, a special design pendulum. And then what we want to see the deflection on the pendulum when we have this laser interaction on these materials. And then you can see the conditions on Perla-B experiments. So you can see here the spot size, the kind of energy we use per pulse. So it was from 3 to about 10 millijoule per pulse. Then we did repetitive experiments. So we have pulse number from 1 to 100 because we want to see what is the effect of repetitive pulse on our experiments. And then all these experiments were done with a special vacuum. Then here is the pendulum. So what was the pendulum? As you can see on the left side, the pendulum is just systems that it is can hold the polymers, as you can see with this black part, and then we can give mobility to this pendulum when we have these laser materials interactions. So when the laser will shoot the polymers or the metals, then he will give mobility to the pendulum. And by following this mobility, this velocity of deflection, the angle deflection of this pendulum, where we're able to come back and to calculate what we call the momentum coefficients. And then to follow this deflection angle of a pendulum, we use what we call Doppler velocity, and then we can optimize this mobility with some calculation and solving some dynamic equation. And here you can see the illustration of a team when we did all these beautiful works. So you can see all the team, and on the right side you can see the pendulum that we use. So this pendulum was fabricated with additive manufacturing, with PLA, polymers. You can see the holder with the sample, and then it was suspending, as you can see, inside the vacuum chamber. And then you can see the right point, the laser point. This can give us the following of this velocity of a pendulum. Then now I will show you the first experiments about can get. So the first idea was, okay, how to calculate this CM and what was the influence of the increasing of a number of pulses. And of course, for a CM at a constant fluence per pulse. So you can see here on this figure, you can see that we analyzed 3 samples. It was aluminum, it was this polymer, this POM polymers, and we developing and fabricated POM aluminum polymers. So it was at 50% per weight aluminum blend with POM. And then you can see here the different conditions. So in red, it is aluminum part. In blue, it is for the POM polymers. And in green, it is this hybrid polymers with aluminum. So then you can see that we have energy per pulse. For aluminum, for example, we have 2 energy, 30 kilojoule per metre carré per pulse, and we have about 300. And you can see that according to the number of pulse that we are able to impulse on our target, you can see that for aluminum, we do not have a big influence of the number of pulse on the CM of the aluminum. We have something almost constant. Just at the beginning, we have a lower of the behavior. But what is very interesting is about the POM aluminum connections and behavior. You can see with the POM aluminum, we're able to obtain a maximum of efficiency of the CM, and the maximum is reached when we have a number of pulse of 20. So it means that when we want to give mobility or higher power to a target, maybe it's not need to give too much number of pulse, but we have also to define what is the number of pulse that can be the optimum that can be used to have the CM. So this experiment was very important for us because it was possible to find this tendency and then to always see that we have to optimize all the conditions, not only the energy per pulse, but also the number of pulse. And too much number of pulse will not give us the best result or the best efficiency. The second illustration that I want to give you today was also, we keep here the constant number of pulse. So we decided to use 100 pulse, and we decided to change the fluence per pulse and to see what can be here, no more the number of pulse, but here the fluence per pulse. And then it was very surprising and very interesting for us to see that when we keep the number of pulse constant, for here it was 100 pulse, and then we increase the fluence per pulse, we can see that also for aluminum, we do not observe a big change or a big influence of the energy per pulse according to the aluminum. So no need to put too much fluence on aluminum, for example. It will not give us much behavior on CM. But for POM aluminum hybrid systems, we can see that we have an optimum that we can reach because, for example, if we have a fluence per pulse out about, I will say 17, we can reach this maximum. And then if we increase this fluence, it will not increase much these coupling coefficients. So here we can see that according to the materials that we will use, we'll have a special behavior according to the energy. So it means the fluence per pulse that we will have, and also the number of pulse that we can apply at our targets. So it's very difficult to have a kind of general history. You have to always connect materials with the energy on laser ablation. So we have always to find on laser and energy, of course, but also on materials. It is a combination of these two systems that can give us the possibility to propulse and to develop new propulsion systems. And then at the introduction, I'll speak about the possibility to damage the systems, our targets, because when we shot the polymers, for example, here the POM or the POM aluminum, so when we have this velocity, it means that we can have ejecta. And also this ejecta can be a problem because we want to avoid to have too much debris. But if our laser ablation gives too much debris, we do not solve the problem. So we have to take care also about what kind of debris the laser ablation can involve during the experiments. So as you can see on these illustrations, we selected to use high energy conditions. So it is these 30 kilojoule per mètre carré per pulse. And you can see on the right side on the picture that we have a small damage of the surface. It is still small damage because you can see that we have a change of the depth from 40 to 200 micrometers, so we damage the surface. So it means if on the same surface we shoot again with a laser, it will be not the same samples because it is not the same surface. So maybe the CM can evolve also. And then you can see that during these shot interactions here, if you use the aluminum target, we can see we have a droplet. So it means that we change the state on the systems. So the aluminum was melted and then induce some droplets, and these droplets was ejected and some was again solidified on the surface. And then it means that you can change also the kind of chemistry on the surface on the sample. So you can see that when we analyze all this combination of energy and materials behavior, you can see that we have a very nice result when we use polymers, when we use hybrid systems. So for example, aluminum with polymers. For example, in our case, it was POM polymers. But also you can see that we change the state and the surface, our surface. So this also can change the CM analysis. So to better understand what can be the effect, we need to always repeat the experimental conditions, but also to think about simulation and to think about phase transitions of the materials that they are in interaction with the laser energy. So then, when we did this beautiful experimentation with Perla-B, the second idea and open questions that all the team decided to develop was to go further to the investigations and to use BIVOJ energy in order to make a demonstration of space propulsions. So it is the second part of my talk. So here it was the condition of HiLASE BIVOJ laser. So you can see in our case, so you can see the room where we did the experiments. You can see the size and the shape of the spot that we use. So it was a square spot. And here it was the condition of our experiments. You can see the beamline here. You can see that also we use a chamber, and then all these laser condition was focused on materials. So then, because it was the first time for us to use BIVOJ, it was necessary to give a kind of schematic rules of materials behavior. So for that, we did our experiments with two lines. The first line was to check about the damage of our polymers, and the second one was how to make propulsion on our systems. So first, let's see about the damage, what was induced because of laser materials interactions. So here you have an example about a condition that we selected. So it was 10 nanoseconds, as you can see. So you have all these frequency energy. Then we did a single shot, and then we did multiples on the target, so that's target. So at first, you can see that when we apply multiples on the surface, so here I selected, for example, polymers, because we are concerned about polymers, because for us it's a good candidate. You can see that when we apply too much energy with repetitive pulse on the surface of the polymers, of course, we damage the polymers, and we could not have any more effect of propulsions because we have no more polymers. So it was very important for us to define the best condition to avoid this damage. And then you can see that when in the same condition we apply only single shot, then here you can see that we destroy a little bit the surface of the polymers, but still we can use this surface to apply again a shot on the surface. So here we try to define what was the mass loss according to the thickness of the sample, because we selected different kind of thickness to see what can be the limitation of the design of the materials that we can use for the demonstrations experiments. And then you can see that with prom aluminum, we can define big, more or less best conditions with 1 millimeter thickness of target and a mass loss that it is not so important. So it means we have a systems that will not involve too much debris. So it means it's a good candidate, as we can see in the literature, to use these POM polymers in order to define the best demonstration design. So now, to finish my talk, I will show you a demonstration about the laser ablation and how to give mobility, to give velocity on systems. So here in HiLASE and on the BIVOJ line, we developed a big V-rack, as you can see here. So the size is about 4 meters length. Of course, we work at atmospheric pressure, okay? And also, we decided to use this rack horizontally, but also with a tilt. The tilt of about 5.6 degrees, because the idea was to see what can be the effect of the inclinations to the velocity on our target. And of course, all these experiments was done on a polymers, and for that you will see here the first illustration about what we did. Okay. So you can see that the laser is shooting from the left side. You can see the eye, and you can see that the polymer ball is going from the left to the right side. So we can see that for each shooting, we have what we call an ablation. Okay, you can see again. So you can see that we have ablation clouds. Each time we have a laser materials interactions. So of course, we have an open questions when we observe this kind of behavior, because the open question was, okay, if these ablation clouds can be absorbed by the laser and have a lower effect on the laser ablation. So it was one open question that we wanted to check. So here you can see different stage on these experimentals. So each picture I wanted to show you at the beginning of experiments, and each time that we shoot on the sample, you can see that these plume or these ablation clouds that we can see each time we have these laser interaction with the target of polymers. So then let's see about this effect and if we can have first conclusion about this demonstration. So here I want to show you two experiments, two conditions. So the first one and the second one. It was the same conditions, so the target of the ball of polymers was about a diameter of 40 millimeters. And see, you can see the energy, what we put on the surface. So for the first experiment, it was about 0.20. And for the second one, it was about 0.123. So then the first conclusion that we can say is when we increase this energy, we increase the velocity. So the higher energy that we'll have on the surface, the higher the velocity we can be induced on the target. So it means that when we control the energy on laser ablations, we are able to control the speed that we want to give us on our target. So this was the first demonstration. The second demonstration that we want to see was about the frequency. What can be the influence of the frequency on this behavior, on the velocity on our systems? And here you can see on this figure different kind of condition that we use. For example, if we look at the first experiments, the number 5, so you can see that we have 1 hertz, 1 pulse. So how it works? So at the first pulse, we give velocity to our target, and then you can see that the target will lose the velocity. So then we can see that we can control at the first shot the velocity on our systems. Now, if we apply, for example, 10 hertz and 30 pulse, so it is the number 4 in the figure. So you can see that when we have at 10 hertz repetitive pulse on our ball, that it is ongoing, you can see that we have a constant velocity that can be applied to our target. So it was very interesting for us to see that we are able to induce a constant velocity when we apply repetitive interactions and cumulative repetitions on our target. Then, if now we look at the experiments number 3, so it was 10 hertz, 12 pulse. So, of course, it is a combination, more or less, of the experimental number 4 and number 5. So you can see that we apply 12 pulse at 10 hertz, and then when we stop the end of a pulse, you can see that from a constant velocity that we can calculate, then you can see that the ball will lose its velocity. So you can see that with these all conditions, we are able to control what we call the behavior of the velocity of our system. So this one was very nice to have as a demonstrations because we are able to manage more or less the kind of velocity and also to the degrees of velocity on our target. And then some things that we wanted to compare, it was about the 1 Hertz conditions and 10 Hertz conditions, because just before I told you about this ablation of plume. So we wanted to see if this plume ablation will have an effect or not of our systems or laser parameters, laser interaction behavior. And we see that most probably we can have an effect of these plume ablations because we can have a kind of not clear atmosphere that can be induced because of these small debris or small cloud. So it means that if we want to have a better control of these ablation systems, we have also to keep in mind that to have a better efficiency, we have to also to take into account this apparition or these creations of these cloud systems. Then let's go to the last demonstration part we did. So here is when we give a tilt in our VRAC system. So you can see here, as the same before, on the left side you have the laser and the laser material interactions that give mobility to the ball, and you have also the inclination here of the rack, and you can see that we have a kind of ping-pong effect. So you can see that we have a velocity, then the ball is going up and then go down, up, go down. So it means that when we have this kind of demonstrations and when we have also inclinations, it means that we are able also to give a kind of ping-pong effect on our targets. So it means that we are able to have increasing velocity and to have a decreasing velocity on our targets. So this one also is important for us because it means that we can give accelerations or deceleration in our systems. Then, to conclude, so with this BIVOJ effect, laser experiments, so we are able to do these BIVOJ experiments because we could prepare these experimental setups with the CM calculations that we did on a Perla-B experimental setups. And then we are able to make this kind of demonstrations and see now that to make these laser ablations, it's very important for us because they can give us new opportunities to better control more or less that we can have in space debris propulsions. So it is very nice result. And these nice results were possible to get because of Laser Lab Europe. So thanks so much to Laser Lab Europe, to HiLASE, and also to CNES, and to all the team from France, Sonarless, and also from Claude Phipps from USA, because all these beautiful works was possible because of this beautiful team. So thanks so much.